Hi, this is Angela Galloway, and this is a lecture video for STATS 220. And we are finally in chapter 10, which is the last chapter of our statistics class. So this is the second chapter for Unit 5. We do chapter 9 and 10. So chapter 10 will probably break up into at least two lectures similar to how we did with chapter 9, because first we're going to talk about proportions, and then we'll talk about means similar to how we did with confidence intervals. But first, before we get into the actual sections for chapter 10, I kind of just want to um, give you an idea of what we're trying to do in this chapter, like the concept of what we're doing this for, why we're doing hypothesis tests. So chapter 10, we're talking about hypothesis testing, and so there is going to be a lot of new terminology that we use for this hypothesis test. So we kind of have a lot of build up just to finally get to a real example, because we just have to learn a lot of different things before we get to that. Even though we're still using, normal probabilities, we're using the z-score like we've done before. We're using alpha similar to how we have before. So we're using a lot of things that we did before. We just are using them in different ways. So often, with inferential statistics, what we're doing that for is to make decisions or judgment about the value of a parameter, like a population mean, for example, right? So in the restaurant example that we did, that was one that I did in class. If you're taking an online class, I just kind of explained how we did that. But in class, what we did was I gave all the students a list of 125 restaurants, and I had them all numbered, and they had their annual sales and then or their revenue. And then I had everybody randomly choose 16 restaurants, and so they did that using random number charts. They all got different answers. We calculated the sample mean of those 16 restaurants, and then from that we created confidence intervals because we were doing it for chapter 9. But when we did that, we all got different sample means. So some of us got high numbers, in the millions. Some of us got low numbers in the 700,000s. They were kind of all over the place. But we saw that they started to center around the 900,000 mark. So then I told the class that the mean for that distribution was actually 911,000. And I knew that because I'd actually created the data. Okay, so I knew that was the mean. But most of the time, when we are doing some sort of study, we don't know what the true mean is, right? We just have our sample and our X bar. So, for that example, if you had happened to get a sample that had a sample mean of 934,000, and then I told you the true mean of the population was 911,000, you would probably think that made sense because your mean was fairly close to what I said the true mean was, right? But if you had been one of those people that had gotten a low sample mean, maybe at $712,000, and I told you, well, the real population means 911,000, you might have thought that wasn't the case because, I mean, your number was $200,000 less. That seems like maybe a lot more than just sampling error, right? So there would be two issues there. You would either decide that you just happen to get a bad sample, which doesn't mean bad in a way like you did something wrong with your sample. It's just there's always that possibility you're going to get a really low or a really high number. Now we said only, 5% of numbers fall more than two standard deviations from the mean, right? But you still have a chance. It's very unlikely to get that. There's only a 5% chance to get something there, but it's not impossible, right? So if you got one of those low numbers, it's either because you happen to get one of those numbers that fell in that low 5% or 0.3% or whatever, or the population mean really isn't what it was stated to be. So maybe it wasn't really 911,000, it was really 800,000 or whatever, okay? So those are the decisions we have to make with hypothesis testing. We're trying to see if something is different just due to sampling error, or if it's different because the parameter that we thought it was is not really that. It's really less than or greater than or not equal to what we originally thought. Okay, so with hypothesis testing, the first thing we're going to do is set up our hypotheses, okay? We have two hypotheses in every hypothesis test. The first is the null hypothesis, which we write as H sub 0. It can be called H naught or H null, any of those, or H sub 0. Any of those mean the same thing. This is the hypothesis to be tested. It's assumed true until evidence indicates otherwise. And for our class, it's always going to have an equal sign. The alternative hypothesis, which is H sub 1, and so we'll say H1 or H sub 1, is the hypothesis that we're trying to find evidence to support. So this is typically the one that we want to show is true. So, we've done some research and we're wanting to show that, our product is better or whatever, so this is what we're trying to show is true. And when we create this hypothesis, it's going to have one of these inequalities, the less than, greater than, or not equal to. Okay, so to create our hypotheses, the null is always going to be the parameter equal to a value. So our parameters that we've talked about are mu and p, right? Our population mean and our population parameter. So they're going to be equal to some value. The alternative hypothesis will depend on what you're trying to prove. So it's still going to be the parameter, okay? It's still going to be the same value. The only thing that's going to change is, are you concerned with it being less than, greater than, or not equal to? So how do you decide that? Well, if in your study your concern is just showing that something is different from a specified value, so maybe you're not even sure if it's greater than or less than, you just are worried that it's different from the original amount, then you would do a not equal to because you're concerned with this lower tail and the upper tail. And so that's why it's called a two-tailed test here, because we are looking at both of the tails here and here. If you're just wondering about less than, then you would use the less than sign, of course, and this is called a left tail test because you're only concerned with the left tail. You're only looking at low values, right? If you're looking at more than, of course, that would be a greater than, and that would be a right tail test because we're only concerned with these high values over here, okay? All right, so let's do some examples setting up just the hypotheses. Now, why it's so important to set up the hypothesis correct is because your calculator can do a lot for you. It can calculate our test statistic we're going to talk about later on, the p-value, and all that stuff. But what it can't do is it can't create the hypotheses. So you're going to have to tell it, this is the test I'm running so that it knows how to correctly calculate your p-value and all that later on. Okay, so we do need to have the ability to set these up correctly so that we can put it in our calculator correctly. So looking back at the restaurant example we started with, if you had gotten a sample mean of 712, then that probably would make you think that the true mean is less than 911,000, the number I told you. So we'd say, I told you the mean was 911,000, right? That's our null hypothesis. But you're trying to prove that the true mean is actually less than 911,000, okay? So that's how we would set up these hypotheses. Number two, for this one, we're looking at a new drug for children, a new antibiotic, and it says 2% of children taking other antibiotics experience headaches as a side effect. The researcher wants to know if this new antibiotic causes more children to have headaches as a side effect. So we're saying this is the what's known for antibiotics, that P is equal to 0.02. We want to see if the new antibiotic has P greater than 0.02. So if that side effect is more than 2%. And then number three, when water treatment plants are monitoring the water there, They are concerned with it being too acidic or too alkaline. So they're concerned with it being too low or too high, okay? So in that case, they really are worried about both tails, right? The lower and the upper tail. So they're just looking for differs from this 8.5. That's what the target pH is. So this is the pH that we want. This is what we're concerned about, it not being equal to 8.5. So every time they take a sample, they would use this hypothesis test, then run the test and see if they are able to reject or fail to reject this. Okay, and then that would tell them if the water was differing from that 8.5. Okay, so that's the beginning with setting up the hypothesis. The last step of the hypothesis test is making the conclusion. This is the other part that your calculator cannot do. Okay, your calculator will give you the data, but you have to figure out, what to do with it. What does this tell me? Does this tell me that my claim is true, or does this tell me it's not true, right? So that's what we're looking for. So at the end, after we do all our tests and calculate, a p-value, some probabilities, all that stuff that we're going to talk about later on, we're going to make one of two conclusions. We're going to fail to reject the null, okay, or we're going to reject the null and accept the alternative. If we fail to reject the null hypothesis, that means that our statistic may have differed from what we expected, but that difference was just due to sampling error. So there wasn't really a statistically significant difference. So maybe they were off a little, but we know every sample is going to have produced different results, and it looks like that difference was just due to sampling error. Okay, so when we look on a chart here, we'd say, if we're talking about mu, let's say, we would put the mu from the null hypothesis here. We're saying this is where we think the distribution is centered. Then we get a test statistic, okay, our x bar, and we're going to just see, how far away was this x bar from mu? If it's really far away, then I say, that seems pretty extreme. So it seems more likely that this is not really the true mean of the distribution. But if it's not that far away, then I'd say, well, yes, there was a difference, but it looks like that difference was just due to sampling error, just due to the fact that my X bars live here in this sampling distribution. They can be, anywhere from here to here, right? 95% of them are within 2 standard deviations. So, if I get one that's 1.5 standard deviations away, it's not that extreme, right? Just seems like happen to get a value a little lower, right? Not really a big deal. And so in that case, we would fail to reject if it's not that far away, because we're saying it doesn't give us enough evidence to say mu is not what we said it was in the null hypothesis. But if it is really far away, let's say like down here, we would say, well, the chance that would happen due to sampling error is really, really small, right? It's very unusual to get a statistic this far away. Let's say this is beyond 3 standard deviations away. So it's very rare for that to happen. So it's more likely that this is not the true mean, okay? Because if this is only going to happen, let's say 0.1% of the time, well, do I think I just got really unlucky and got one of those samples that only happens 0.1% of the time? Or do I think maybe this is not the true mean, and this is actually coming from a distribution that has a mean that is lower than what the null hypothesis said? Okay, and so that's the process that we're trying to decide. But as we're looking at this, how do we decide what is far enough away? Do we say 1.5 standard deviations? Do we say 3? Do we say 2? How do we know? So what we want to do is we want to set up some kind of boundary or limit or whatever that says, anything that falls in front of this is just due to sampling error. It's not really that far away. Anything that falls past this line, then that's where we're going to start to say, okay, that seems really unusual to happen. So I think the mean is not true, okay, or the null hypothesis. We're going to call that the critical value approach, okay? And the critical value approach, we get these critical values from our normal table if we're doing proportions. It'll be from our t-table if we're doing means, just like we did for our confidence intervals. So these are going to be similar to the numbers we used for our z alpha half and the confidence intervals, because our level of confidence and our alpha levels that we're going to talk about um, go together. Okay, if you remember our levels of confidence, it was 1 minus alpha equaled your alpha level. I mean, sorry, that doesn't make any sense. It was 1 minus alpha equals your confidence level, right? So if your confidence level was 95%, your alpha was 5%. Okay, so now what we're going to deal with is this significance level, which we call the alpha level. Okay, that's the same alpha we've been talking about. So this one here in this example, we're using an alpha of 0.05. So we would look at what z alpha corresponds to 0.05, and it's negative 1.645. Now, how could you get that? Well, there's a few ways. Um, the easiest way, the quickest way, if you don't like using your chart, would be to use the inverse norm in your calculator. If you do the inverse norm of 0.05, it'll give you negative 1.645. That would probably be the easiest way. The other way we could do it is, let me pull up on our Blackboard page real quick. I should have had this already. Let me get to this. I'll pause this. Okay, so I got to our Blackboard page. If you go to the resources, the notes and videos, it's also in the proctored exam link. I've got this formulas for final exam, and now these are the formulas that you will take to your proctored exam site, so you have to print them off on your own. But if you click on them, you've probably already been here to look at some of the tables. If you look at the normal table, okay, so this is table 5, at the very bottom here, let me make this, oh, it won't let me make it bigger. I was going to make it a little bigger. But if you look down here, there's confidence interval critical values, which we use a lot when we're doing the confidence intervals back in chapter 9. And then they have hypothesis testing critical values, okay, down here. So it says if your alpha is 0.1, and you're doing a left tail test, so that means you're doing a less than, right? You're in the lower tail, then your Z is going to be negative 1.28. That's going to be your critical value, okay? If you've got an alpha of 0.1, but you're doing a two-tail test, then your Z alpha half really will be plus or minus 1.645, okay? So these values over here, what you would have used like for your confidence interval, because a confidence interval, kind of has those two tails left over. But anyway, so that's where you can go. That would probably be the quickest reference if you don't do just the inverse norm on your calculator. Okay, so that's where those numbers are coming from, just so you know they're not just made up numbers. They're just the same ones we use for our critical values for our confidence intervals, the ones we learned about in chapter 7 when we were just looking at normal probabilities, etc. Okay? So when we set this up using our critical value, it sets up this area here. I didn't really want that. If we do this, it sets up this area that we call the rejection region, okay? If our value falls into this rejection region, so once we calculate how far away our observation is from the mean, if it falls in here, then we reject the null hypothesis, okay? If it doesn't fall in here, if it maybe just falls this far away, then we say it looks like the difference is just due to sampling error, and so we would fail to reject, or we do not reject the null hypothesis, okay? If it's over here, if we reject, that is statistically significant, okay? Because that means there is a difference between the two values, okay? It's far enough away that we say that we think there is really a difference. If it's here, then it's not statistically significant, okay? Because we're saying that difference looks like it's just due to sampling error, okay? It's not really that big of a deal, basically. Okay, so that's how we would define, statistically significant and not, because sometimes students get that backwards, okay? If we reject, then that is a good thing. Usually we're showing that our what we were trying to prove was actually true in that alternative hypothesis. Okay, and I think we kind of already talked about this with significance levels, so you can go back and look through that. But the most common levels of significance are going to be 5, 10, and 1, and those correlate back to our confidence intervals. The 95, the 90, the 99, they correspond back to these percentages because those are our alpha levels. Okay, now when we have made our decision at the end, okay, so let's say we had this here. Okay, we created our rejection region using our critical value, okay, and we got a mean over here. Okay, so this is our mu from the null hypothesis. When we calculated how far away our statistic was, it was over here. It was in the rejection region, so that means I'm going to reject. Okay, if I reject, then that means either one of two things. One, I made a good decision. If I reject the null, and this really is false, it really isn't the mean of the distribution, then I made a good decision. But it's possible, let's say if my alpha is 5% here, let's say alpha is 0.05. What that alpha means is there's a 5% chance that I might reject the null when I shouldn't have, right? Because there's a 5% chance that this statistic is that extreme just due to sampling error, right? Because 5% of the time, some of our samples are going to give X bars this low. So there is that 5% chance that I can make a type 1 error, which means I rejected the null hypothesis because it fell over here, but this is true. It's not false. And so I shouldn't have rejected it. Okay. Um, that's why we want to keep our alpha levels low. That's why we don't use like an alpha of 30% because that basically says there's a 30% chance I'm wrong. Well, I don't really want that, right? So I want a low alpha level. So that's why we keep it at 10 or below. 10 is going to be kind of the highest alpha level you're going to see. So I keep that alpha level low because I want to try to keep type 1 error at a minimum, okay? Now there's also the possibility that I could, let's say, get an X bar here. So it's not in the rejection region, okay? So if I get one here, that means I'm not going to reject the null, right? I'm going to fail to reject the null. If the null really is true, then that's a good decision, right? Because I shouldn't have rejected it and I didn't. So that was good. But it's possible that I got this result and I really should have rejected the null hypothesis. So maybe I got this one here. It wasn't that extreme, even though it was, lower than the mean, but it wasn't far enough away for me to be able to say that the null hypothesis wasn't true. So that would be a type 2 error when that happens. And that's called a false negative. So if you're more in the medical field, you may have heard like false positives, false negatives. So we're usually more concerned with the alpha as compared to the beta. Alpha is our type 1 error. Okay, like I said, if our alpha is 0.05, that means you have a 5% chance of making that type 1 error. Our beta is the type 2 error. So that's the chance of a type 2 error, which is really just the opposite of alpha. Okay, so for a fixed sample size, the smaller we specify the significance level alpha, the larger beta will be. Okay. Here's just a quick example comparing type 1 and type 2 errors to criminal trial. Sometimes that helps students to kind of understand type 1 and type 2 error, but you can look through that on your own. But one thing I kind of talked about with my students was when we're thinking about type 1 and type 2, false positives, false negatives, when somebody, if we're trying to find out if a patient has cancer, is it worse to tell them that they do have cancer when they don't, or to tell them they don't have cancer when they do? Okay, to tell them that they do have cancer, when they don't really, would be more like a type 1 error, right? That's going to be a false positive. That's what we're usually more concerned with in our test. The type 2 would be telling them they don't have cancer, but they really do. Okay, now that would also be a bad situation, but in most of our problems, we're more concerned with this happening. So, it kind of depends on what you're running, what kind of test you're running. Maybe you are more concerned with the type 2 error, and so you might want to make sure, you prevent that from happening as opposed to the alpha. But just in most of the tests we do, we're more concerned with this up here, okay? All right, so now we're finally into section 1. Okay, all that was just kind of the preliminary work. So hypothesis test for proportions. These are the important critical values, and this is really just similar to this thing over here that we already looked at. It's just one I had written out, okay, but they're the same values. So either one you want to use is fine. Okay, so the steps we're going to take when we do this, first we're going to write out our hypotheses, okay, the null and the alternative. Then we're going to decide on a significance level. And what I mean by decide, in our homework problems, you're not really going to decide. They're just going to give it to you. But in real life, you would have to decide basically how confident do I want to be? Do I want a really small alpha level or do I want it a little bigger? Just decide on that. But these will be given to you in your homework problems. The next thing we're going to do is compute the value of the test statistic. Our test statistic here is going to be a z, okay, right? Because we're trying to see how far our observation falls from the mean. And how did we do that? Well, we learned in chapter 7, and really we actually learned back in chapter 3 is when we started using the z-score. But we learned that, when we're in the sampling distribution of x bar, if we want to tell how far away this thing is, we just calculate the z, right? And that z then we can use to calculate probabilities or whatever as we need. Determine the critical value. That comes from alpha. That's just these numbers here. Okay, so just like when you were doing your confidence interval in chapter 9, that z alpha half would be based on your confidence level, right? You just go look it up and use it. The same thing here. When you know your alpha, then you can set up your critical value. If the value of the test statistic falls in the rejection region, then you reject the null. Otherwise, you do not reject. So once you calculate the critical value, you compare your z to the critical value, see if it falls in that rejection region or not, and then make your conclusion, okay? Now, what is our test statistic going to be? Okay, we have a z here. And actually, I was talking about means up here, but I really should have been talking about proportions. Let me change that. So we're really thinking about p and p hat. Okay, so we've got this test statistic. Now it looks kind of big and scary, I guess, when you first look at it. But what I try to explain to my students is really all we are using in chapter 10 is this formula right here. The formula we learned back in chapter 3 that I said, eventually this is going to be a very important formula to us, okay? And it is. We've used it a lot in chapter 7, 8, 9, and now in 10. So the Z formula, right, tells us how many standard deviations our observation is from the mean of the distribution, right? So the original formula we started out with was z equals x minus mu over sigma. Now, how can we transform that into something we can use in this situation? Well, first we want to think of where is our data. We're looking at data that is in the sampling distribution of p hat, right? So inside the sampling distribution of p hat, what are all the observations there? When I pull out a number, what variable is that number? Well, it's a p hat, right? Everything inside of this distribution is a p hat. So my observation is now a p hat, not just an x value, right? Now, what's the mean of the distribution? Well, the mean of the distribution, it's centered at p, right? And the p that we're talking about here is p sub 0, which is the population parameter that is in the null hypothesis. So p sub 0 is just coming from the null hypothesis, okay? Then what's the standard deviation of this distribution? Well, it's the square root of p becomes 1 minus p over n, right? Since we're using p sub 0, we'll plug those in there, and that's what we're using. So that's how we get to this formula, okay? It's really just from this basic z formula we had a long time ago. All right, so let's do a problem here. Okay, Kentucky's unemployment rate was 5% in March 2016. A local politician wants to see if Warren County's unemployment rate is statistically lower than the national average. He takes a random sample of 1,000 Kentuckians from Warren County and finds 41 are unemployed. With a 5% level of significance, does this sample provide enough evidence to say that Warren County's unemployment rate is statistically lower than the national average? Okay, so we've got this set up here. We need to figure out our hypotheses, find the test statistic, do the critical values, and then make our conclusion. Okay, so our null and alternative hypothesis, they're both going to have a p here, right? Because that's our parameter, not p hat. We want to have the parameter in here. Okay, so it's p. In the null, it's going to be p equals to something. So we're comparing this to Kentucky's unemployment rate, right? So Kentucky's unemployment rate, it says, this was back in March, was 5% in March 2016. So we're going to say P is equal to 0.05. Now we're trying to see if Warren County's unemployment is better, okay? And in this case, better would be the lower than, okay? So we're going to do P less than 0.05. All right, so for our test statistic, that z equals p hat minus p sub 0 divided by this big square root thing, right? So to get my p hat, I'm looking at how many people from Warren County were unemployed, and it was 41 over 1,000. So I calculate my p hat, so it's 0.041. So we can see that that 4.1% is definitely lower than 5%. But we're trying to see if that difference is just due to sampling error, you know, like maybe just the sample happened to be lower, not really enough evidence to show that it's different, or if it actually is statistically different from the 5%. So we plug in this value here, 0.041 from there. The p sub 0 comes from our null hypothesis of 0.05, and then we plug that in here again. And this equals negative 1.31. Okay, now calculate our critical values using this 5% level of significance. So that's our alpha. So alpha equals 0.05. So we would go back, you know, we could go back to our chart here and say I have an alpha of 0.05. And a one-tailed test, so I'm going to use 1.645. And then if we're doing a left-tailed, it's going to be a negative number, okay? So you just take that and make it negative. So it'll be negative 1.645. And so if your z-score falls below negative 1.645, then it's going to be in the rejection region. Our value of negative 1.31 fell right here, right? So it did not fall in the rejection region. So that means we would fail to reject the null hypothesis at alpha equal 0.05, which means that Warren County is not significantly lower, okay? So yes, we did see a lower result, but there's not enough evidence to show that that's not just due to sampling error, okay? It didn't fall far enough away from that null hypothesis. Okay, here's another example. This one we're going to do a two-tailed test. So it says researchers are wondering if people prefer Coke to Pepsi. They're going to assume that the claim to be tested is that there's no preference for Coke over Pepsi. They do a random sample of 500 adults and 275 of them chose Coke over Pepsi. Is that significant at alpha equal 0.1? Okay. So to do this one, when you see the no preference or just something that says you're just looking for a difference or differs, that usually clues you in that you're doing a not equal to down here. Now, where did I get the 0.5 from is what most students get confused about. On this one, it says they're going to assume the claim to be tested is that there is no preference for Coke over Pepsi. So what that would mean is that it's just 50-50. You know, it's just kind of split half and half. There's not really a preference either way. So that's where we get the 50% from. So P equals 0.5. The alternative is P not equal to 0.5. Our test statistic here, we got to calculate our p-hat. So we plug in the 275 over 500. We get 0.55. So we plug that in here. We get 2.24. Our critical values, because we have an alpha equal to 0.10, that means that we want 0.05 in both tails. But on our chart, we can look up, alpha of 0.1 here. We're using two-tailed alpha equal to 0.10. That's a 1.645. So we use the positive and the negative. So in this tail, it's negative 1.645. In this one, it's 1.645. So we've set up our rejection regions. We see where the 2.24 falls. It falls in this red area, right? So it's in the rejection region. So that means we would reject the null hypothesis at alpha equal 0.10, okay, because that's our alpha level, and accept the alternative hypothesis. So what does that mean? Well, it means based on our sample, it looks like there is a significant difference in those who prefer Coke over Pepsi in this example we had, okay? Okay. So I think I'm going to stop this video here because it's already been long enough probably, so you can soak in some of this stuff, and then I'll make another video. What we're going to get into next is how to do the p-value approach. So we really have two approaches to solving these problems. The first is this critical value approach, which I think makes a little more sense when we're starting out, so you can see because when you draw this out, you can see that this falls far away, farther away than what we expected, so we reject. With the p-value approach, once we get this test statistic, we're going to look up the corresponding area. So, look up that area that we would have found like back in chapter 7 or 8 when we are just looking at normal probabilities. And so we did the area, gave us the probability or the percentage of the data that fell in a certain part of the graph. And we're going to use that to compare to alpha, and that's going to tell us whether it's far enough away or not. Okay, so it's just another method. Now, why students sometimes like the p-value a little better is because we can do that one in our calculator. So we can use our calculator for that one. But the conclusion still has to come from your own mind. You can't get that from the calculator. So you do still have to do some of it by hand. You have to be able to interpret the results. Okay. All right. So I'll start that in the next video. If you have any questions, please feel free to email me at angela.galloway@kctcs.edu. Thanks.